Okay, so now a 4-vector, we defined scalars. Okay, on the previous part of the lecture, we defined scalars. So what's a 4-vector? Well, a 4-vector basically defines the separation between events in space-time in 3 plus 1 dimensional, 3 spatial, 1 time dimensional space-time. So, for example, if we have two events A and B, okay, that I'm showing here on a space-time diagram, then a 4-vector basically defines their separation. Okay, and we can write this separation. We can give it a notation big X. Okay, and we're going to put an arrow above it to denote that it's a 4-vector. Okay, when we have to write three-dimensional vectors, spatial vectors, we'll have to use some other notation. Probably what we'll do is just we'll denote anything which is a 4-vector as a capital letter. Okay, so this is equal to, we can write the 4 components of this vector like this. Okay, and we did this before when we were deriving the Lorentz transforms. Okay, and the thing to note is that this is actually sort of invariant. A 4-vector is invariant in different frames, although the components are not. We know that delta x, delta y, delta z can be different in different coordinate systems, okay, different reference frames, and so can delta t. So the components of the 4-vector are not, but the 4-vector itself is invariant in just the same way that a normal the distance between 2 points in three-dimensional space does not depend on the coordinate system. So if you have a rotated coordinate system, then the distance, the coordinates for each of those points will be different, but the distance that you measure between the 2 points is the same. So in special relativity, we can sort of think about this in terms of, if we boost to a different frame that's moving with respect to the first, and remember that one way we can do that is just by one way we can depict that is by shearing the coordinate system, then this vector between A and B doesn't change. Okay, the coordinates that you measure in this S prime frame, in this boosted frame, will be different, but the vector itself doesn't change. So this 4-vector, okay, X here, is frame independent. It's invariant. Okay, that doesn't mean it's a scalar, by the way. It's clearly not a scalar, but it is invariant from one frame to another. Okay, so the 4-vectors have important quality that they're or important property that their components are transformed from one reference frame to another via the Lorentz transformation. So so that means obviously that that allows us to connect the components of a 4-vector from in one reference frame to another. So we haven't talked about in this class, and we won't, but you should know that in general, when you transform from one reference frame to another, in addition to having one they can move, in addition to the possibility that they're moving with respect to each other, they can also be rotated with respect to each other, in which case you have to include, of course, more complicated transformations than just the Lorentz transformations. So if you include both Lorentz transformations and possible rotations, then you have a more general class of transformations that are called the Poincare group. And we're not going to talk about those in this class, but they're there. You should know that they're out there. Finally, the dot product between two 4-vectors can be defined as follows: A dot B, where each of these are 4-vectors, is just the product of the 2 time components minus the product of each of the spatial components. Okay, so this minus is different than what we see with a normal dot product of normal vectors, but that's how we define it. And this is a scalar. And this, if you look at this, then if we take the 4 vectors defined here and we dot it into itself, we get the invariant interval, which is a scalar, as we've discussed before.